Okay, so what I'll do today, it's kind of honest work. There's lots of algebra. I don't think it's good to do it in public. So I'll kind of skate through it, but the algebra that I do is done in detail in textbook, Strogatz's book. In the excitement of Nobel Prize, I was very, very happy. I started Hopf bifurcations, but they're so important that I will repeat it. And then I'll make a diversion, side diversion. I keep telling you that I'm trying to emphasize topics by how useful they are when you are in 60,000 dimensions and not 2. And that's also true in today's lecture. But then I'll give you a very short introduction in what happens in 64,000 dimensions, just to have some feeling. You're not expected to know this stuff. It's just something as a motivation. Hopf bifurcations, I genuinely think that requires 2 dimensions. All other bifurcations were morally one-dimensional, even though they also can be seen in 2 or more dimensions. Hopf bifurcation happens first time, and mathematically it's for a simple reason. To have complex roots, you have to be in real and imaginary. They have real and imaginary, so the representation in terms of real numbers, it has to be at least 2-dimensional. So they only show up here. Those bifurcations are different than the ones we saw before. The ones we saw on 1-dimension line or last week have a property that pairs of points, equilibria destroyed and created together. They kind of eat each other. And in pictorial understanding, I think about what happens in nonlinear systems. In linear systems, lines cross at one point, or they don't cross if they're parallel, or they're in higher dimensions than 2 and just don't happen to cross. In nonlinear system, you have things that are folded. The simplest examples are parabola. And when a nonlinear stable, unstable manifold, which is some curved thing in a state space, when they cross, they do it by a tangency, and then they, penetrate each other. So you have 2 equilibria, because parabola can be cut by a line in 2 places, or any quadratic, and then, so that's why they come in pairs, appear, disappear. Then you do a little analysis, and you understand pretty soon that close to bifurcation, one has to be stable, one has to be unstable. And that's true even in many, many dimensions. So what happens in many, many dimensions, you might have, a 1-dimensional attractive but curved space crossing a very high dimensional surface. But again, it'll just puncture it at 2 places. Hard to visualize, but yeah. And that's a typical thing. And so that's geometrically easy to understand. Now, Hopf bifurcations are the stupid things that we always see, but naturally they're described in terms of, all oscillations are naturally described in terms of complex numbers, this imaginary phase. And that as humans, we already don't see. I mean, we get used to it, but we don't see it. And for me, there's kind of cost to that, in my own work. I admit to the following thing. If you give me some dynamical systems and, I can get some geometrical intuition about it, and I can find out where equilibria are of that system, points that don't move in a direction as time evolves. I need to know what their neighborhoods do. That's done by linearization and study in this particular set of examples we have seen so far. Study of velocity gradient matrices or stability matrices. These things have roots, characteristic equations for them define all the eigenvalues and eigenvectors by finding the roots. And these eigenvalues are either real or complex. And as far as I can tell in my experience, it's a 50-50 chance they'll be real and complex. And already here, usually, I personally don't have any intuition. I have to do calculation and say, this is complex or real. So I'll come back to it. But basically, whenever you have a real quadratic equation, the simplest case, with real coefficients, and that means, we are sitting in our real space specified only by things we understand, meters, inches, seconds. Eigenvalues and eigenvectors can be real or can be complex, and there's nothing you can do about it. That's fundamental theorem of algebra. You have to go to complex space to understand all roots of polynomials. And when you're in this complex space, it's natural. There are two ways of thinking in real imaginary part, or you can think in the magnitude of the number. So you compute it multiplied by its complex conjugate, take a square root, that's the radial distance on that plot, and the angle. So, there is two representations. And in our world, we tend to think Euclidean way, but, some problems naturally have these polar coordinates. What these complex numbers mean, and you learn it by doing some algebra and some sines and cosines, they have natural two-dimensional representations in terms of sines and cosines, and that's what we observe in laboratory. And in case of Hopf bifurcations, what has happened is we had an equilibrium, and then its stability changes. So that equilibrium doesn't disappear, and sometimes it's always there. It starts out as being an attractive sink equilibrium. Typically, when you first discover it, often just death, nothing happening, or if you have some balance of energy in and out, something that's not dead but not moving, but it's attractive. And then as you start, pushing, stretching the system, making it more nonlinear, subjecting it to more stress of some kind or other, at some point, eigenvalue, and I'll show you examples, go from being negative to being positive. Or if there were negative real part and complex rotation, they would look like, a damped oscillation that dies out. And after some critical point oscillations, when you perturb the neighborhood, they explode. They tend to exponentially go away. And what happens is, in your mind, you think of dynamical systems when you build them, mechanical things like pendula. You think of them as a families with different parameter values. So you think of a pendulum, you change the length of the massive particle, the distance from the origin. And for you, this is mentally always a pendulum. So you naturally think of families in terms of parameters. Now, what one learns when one starts thinking seriously about long-term behavior of dynamical systems, that things that you think are families often are not families at all, in the sense that you can change some parameter value by epsilon, and suddenly have a totally different qualitative behavior, because Poincaré says whenever you're giving a system, draw some pictures or some computer simulations to understand the shape of possible solutions. And what happens is that those guys, sometimes they are in a family, you change it a little bit, nothing changes. So this is typically what happens when you have single attractive equilibrium or a single attractive limit cycle. You can change the system and it moves precise position of the equilibrium in your phase plane or state space, or it changes the shape of your cycle, but it's qualitatively still the same cycle. It's just a little bit stretched and rubberized. So that's kind of, our usual way of thinking. Fine equilibrium, find all of its periodic points, move it around, and there'll be some critical value where it goes from stable to unstable in phase space. That'll mean from spiral in to spiral out. In my mind, because when I solve a random quadratic polynomial, as far as I can tell, there's a 50-50 chance that it has complex rather than real eigenvalues. This just has to do with, square root of trace minus 4 times determinant in this formula. And, there's nothing that says one of these guys is more important than the other. So both things can happen. It turns out Hopf bifurcations are very, very common. And they happen a lot in celestial mechanics, in other kinds of mechanics. So typically the way you see them is that the system that you're studying suddenly develops small, vibrations. That's a lucky situation when vibrations don't explode. But interesting enough, they're very important in lots of chemistry. We'll work out a chemistry example or biophysics. For example, Professor Wiesenthal here has written very interesting papers about how the ear works, the hearing. And the way it works is that your hearing hairs are kind of poised on the limit of a Hopf bifurcation, meaning that if you excite them a little bit, they'll, explode. They'll go in a very different state. So you can use, biology uses these bifurcations in neurophysics, in cell biology, in lots of settings, as a ways of getting tunable and very sensitive, systems, sensors that respond to stuff. It's natural in case of Hopf bifurcations to go into polar coordinates around the equilibrium because you have rotation. And the simplest models look like this. In radial direction, you're sensitive to sign of this parameter mu. If it's negative, then the behavior is expected to be stable. So equilibrium point itself is stable. If it's positive, then things will explode. And when that happens, you have to capture them somehow. And that you do by taking higher power of the radius, here r cubed, which when r is sufficiently far away, manage to balance the expanding term, and when r is very large, a damping because this is a negative sign. And in simplest models, for example, non-trivial ones, you rotate, but in the angle you have some dependence on the radius, not necessarily in the radial component. So this kind of model will have, when mu is small, everybody is just going to run in because negative, because this is negative, and r is by definition a length. It's 0 or larger. So everybody runs in. But when mu is positive, in just radial direction, there'll be a point where mu balance this, and velocity will be 0. So mu will be, when r square equals mu, you have equilibrium in radial direction, but this is two-dimensional system that's running around. So in rotational direction, you will rotate. And now you'll be in a situation where the equilibrium is unstable, you spiral in, but in a plane, when you get to this attractive cycle, you cannot cross it in a plane, so you'll sink in. And if you're any place outside, you will think, aha, this origin is attractive because this is very long damping, so I want to decrease my radius. But when you come to the cycle, you will converge to the cycle, and that's really a limit cycle, attractive limit cycle. And nonlinearity will show up in the fact that as you go around, you speed up, your frequency changes as you change your other parameter B, which has to do with large oscillations. So that's the simplest example. And now, that's just in terms of words, but whenever you have equilibria, you have to compute the matrix of velocity gradients. It can be done in radial coordinates, but it's really more convenient to do it in the Cartesian ones. And you know how to go from angular to Cartesian. Just project onto the two axes and get sines and cosines. Then if you take a derivative of this thing, by chain rule, either you pick up the time derivative in radial direction, or you pick up time derivative, which is derivative of cosine. So you pick up sine theta. By chain rule, you get theta dot here. So angular velocity. Now we have formulas for r and theta. So we just stick them in. This is mu r minus r cubed, this guy, cos theta minus r. This is just omega plus br squared sine theta. I take r out. So I get this to be proportional to mu minus r squared. R times cosine is x. This also has r in it, so this is omega plus br squared, this term, times y. Now, close to the origin, the important part, so at the origin, if you want to compute stability of this equilibrium at the origin, you pick up, this is at least second order in x and y, so you pick up mu x minus omega y plus order, cubic or higher. So not important in the neighborhood. And if you repeat this, you'll get a very similar thing. These guys, you get sines and cosines. So you end up with omega x here, uy here, plus order cubic. And now this matrix of velocity gradients picks up mu on the diagonal and gets minus omega omega on the angles. And this is proportional to unity, and this will turn out to be proportional to general rotations if you think that way, but if you don't worry. You can immediately read off in this simple matrix the trace and determinant and compute the eigenvalues from the usual quadratic formulas. and they are mu plus minus I omega. So mu is a real number, omega is a real number, and they have interpretation of exponential decay or exponential growth, the rate for it. And omega is 2 pi over period of one rotation in the complex plane. So this is frequency. So that's what happens around the origin here. And what happens when you get to the cycle, we will do later, because in the next lecture, we'll start thinking about stability of periodic orbits, not just equilibrium. That's called supercritical because as you increase your parameter mu and you go through criticality, what happens is that your original point, equilibrium, changes stability, and you give simultaneously a birth of arbitrarily close orbit that depends on the value of mu, which as you increase your parameters, that gets bigger and bigger. So you go from a stable equilibrium to unstable equilibrium and stable limit cycle. So that's kind of what you intuitively expect. And experiences, it just says, I'm stressing my system, and it starts vibrating, first slowly and then faster as I stress it. Now, there are systems which have, instead of decay here, they have growth. Those systems, when mu is positive, would explode like crazy because these things won't balance themselves. To mimic the real world, when you're not allowed to move at neuronal speed larger than the speed of light, or you have limited energy to burn, then one has to put in an extra phenomenological term, and their roles. This term is destabilizing because it increases the distance from equilibrium. And this one has to kick in and stabilize the system. What is the flow like? The orientation depends on, omega being positive or negative. If it's positive, we define usually anti-clockwise rotation. So what happens is that if I'm close to the fixed point for mu negative, I don't see the cubic term. It's not important. So I spiral in, everything close spirals in. And now there is a critical distance where these guys balance each other. And that's an unstable periodic orbit. In language of chaos book, it's not a limit cycle because as you go forward in time, you just run away from it. So it's not a limit to anything. But this guy kicks in then. At some point, you run so far away that this term overwhelms these two terms, and you solve some uninteresting equations or do it numerically, and you find out that there is a limit cycle. If you're on the wrong side of the unstable periodic orbit, you're pushed away because it's unstable, and you get close to this. And if you're any place very far and you're exploring this, you never discover there is a stable attractor equilibrium in the middle because you'll be doing that. I have some issues about this because in higher dimensions, it's very hard to find this unstable thing, just like it's very hard to find unstable fixed points. But limit cycles are limit cycles. So these features will survive even though, this discussion will be very fragile in higher dimensions. So this big limit cycle will be there. As mu decreases, this gets to be less and less repelling. And what that sort of does is it scrunches the whole thing. And at mu equals 0, this unstable cycle merges together with the stable equilibrium and creates an unstable fixed point. And what happens from then on, if you're in a repelling region where mu is positive, no matter where you are, you will always end up on this limit cycle. If you're inside of it, in a plane, you can say that. In higher dimensions, you can't. But you will, fall into it. If you're in a big world, you will also fall into it. So this is a weird bifurcation. Unstable limit cycle, which is very hard to see unless you know what you're looking for, because if you try to find it, you just keep running away or forward in time. So you have to think how to do it. But what happens is that as mu goes to critical value, this thing shrinks and just engulfs unstable point. So now you could say, why are these guys doing that? Of course, there are infinitely many bifurcations. This is boring. However, neurophysics has this kind of Hopfs. You're a serious engineer, you care not an iota about neurophysics. You want to make airplanes. Well, airplane wings can go through such bifurcations and, not oscillate and suddenly oscillate like crazy. And this you might not want. We see it a lot when we study fluid dynamics. So it's kind of thing that you don't think you should care about. It's some mathematical obsession with making a catalog of all possible things that can happen. But actually, nature uses it a lot. Now, is there anything interesting happening as mu equals 0? The border of having this unstable thing or not having it. Could something happen? That turns out to be also quite important. So let's look at our usual model that we have studied many times before of a damped harmonic oscillator. Now, not harmonic oscillator, but pendulum, so something that's driven. For example, Josephson junction cares about such things. So the way you introduce dissipation in such a system is you add a term where you're losing energy. If you compute energy function from this, you're losing energy or maybe gaining energy depending on sign of this guy, proportional to velocity. And there are many phenomenological reasons why this is a good way to think of friction. Now what happens when mu is 0, this term goes away, and suddenly you get a conservative system, because this is a pendulum, where theta, angular angle of the velocity, is what's called axis theta. So this is pendulum angle. And here is the moral tale. When that happens, this is just the pendulum. You have seen the phase spread over the pendulum. You know that orbits are either running in circles at any possible radius until you get too far and you get to the separatrices of pendulum, and then there are running orbits. There are motions of pendulum where it doesn't go left, right, but it just keeps rolling in one or the other direction. It's a conservative system suddenly. So there are no limit cycles. Only thing that you have close to the origin are periodic orbits. This is totally different topology. You know, in this crude sense, I don't mean what professionals like Sam consider topology, but when we draw the phase portraits, this guy has everybody running in circles. Make mu epsilon 10 to the minus 16. Doesn't matter how small you make it. The moment that there is a non-zero mu, everything is totally different because you're either spiraling in or spiraling out, and you only have, you know, equilibrium and one limit cycle at best. So that's a moral tale for your, you know, considerations. You might find it useful. People do this in studying Eulerian energy preserving fluid flows to put numerical friction, you know, just so things converge. So people find it useful to model friction or energy loss or pumping of energy by adding little terms to their equations. But you have to be aware that as far as dynamical systems theory is concerned, which is supposed to describe what happens to the systems at all times, you know, arbitrarily small change of parameter in what you believed was a family, you know, mu going negative to 0 to positive, arbitrarily small change can change everything. And it's physical because conservative systems are very common. Quantum mechanics needs them, and lots of celestial mechanics and mechanical engineering is almost conservative, you know, to very high accuracy. But the dynamics of conservative systems and of dissipative systems is totally different. Just a moral tale. Now, I want to go back to what I think is the most important message of what we have learned. And this is that you have to do two things when analyzing dynamical systems. First, you have to find solutions where nothing happens if you can find them. Second, you have to find so-called invariant solutions. So these are points in state space which under action of dynamics, you know, just kind of permute itself, or but as a set-wise, as sets, they are invariant. The sets are there for all times. Periodic orbits are simplest examples, but then there are tora, etc. There are many other examples. So you have to find those things, number one. Number two, you have to find their stability, and I want to emphasize the role of stability by taking you for a little while from 2 dimensions to, I've forgotten, 65,000 or something.